Good morning, everyone. So today we'll continue the Bode plot example problem. So this is the general procedure for constructing Bode plot. First step, rewrite the sinusoidal transfer function as a product of basic factors in time constant form. Then identify the corner frequencies associated with each one of these basic factors. Then draw the asymptotic lines or straight lines with line slope changing at each corner frequency. And we know that from the basic factors, plus 20 dB per decade for 0, minus 20 dB per decade for pole, plus or minus 20 m into dB per decade for pole or 0 with m as a multiplicity factor, and plus or minus 40 dB per decade for quadratic poles. Then determine the corrections to be applied to the asymptotic plot. Draw the smooth curve for corrected points. Then calculate the total phase angle of J of j omega, H of j omega at different frequencies, and plot the resultant phase plot. So to draw the Bode plot, we took one example, that is J of S into H of S is equal to 54 into S plus 4 by S into S plus 1 into S square plus 1.8 into S plus 36. Okay. So first step, we converted into time constant form. Then we wrote the basic factors, some of the basic factors, and also substituted S equal to j omega. So we completed the step number 1. Okay. Step number 2, we should find out the corner frequencies of all basic factors. So let us look at our equation. So what are the basic factors here? Okay. Sorry. 6 by j omega, 1 plus j omega by 4, 1 plus j omega, 1 plus 0.3 into j omega by 6. Sorry, we wrote something down here. Minus, this would be minus here, minus j omega by 6 whole square. Sorry, this would be plus j omega, right? So I can rewrite this g of j omega into h of j omega is equal to 6 by j omega into 1 plus j omega by 4. Sorry. One plus j omega by 4 by 1 plus j omega into 1 plus j zeta value 0.3 by omega n is here 6 minus omega by 6 whole square. It's clear. Now let us formulate the table for drawing the Bode plot. I'll have to draw the table. Let us start here. First one, what is the factor? Then corner frequency. What is the corner frequency? Then what's the asymptotic log magnitude? Characteristic. Then phase angle. Characteristic. First, let us write the factors. What is the first factor? First factor is 6 by j omega. Next factor is 1 by 1 plus j omega. Then 1 plus j omega by 4. The last one. 1 by 1 plus j 0.3 into omega by 6 minus omega by 6 whole square. Right? Okay. So let us find the corner frequency of the first factor. Do you find any corner frequency? For this, it is of the type k by j omega whole to the power of r, right? So that's the first one. There is no corner frequency. So it is 1 by 1 plus j omega t, right? So what is the corner frequency? 1 here. So now what is the corner frequency for this? It is 4. What is the corner frequency? 6. And zeta value would be 0.15, right? So if you have any questions, you can ask. How do you find the corner frequency? Omega equal to 1 by t. What's the t value? And is t value is 1. So what's the t value here? 1 by 4. So what's the omega value? 4. There also is a t value 1 by 6. So omega value is 6. So we should write all these corner frequencies in ascending order, right? Should write like this: 1, 4, 6, ascending order. Next point is we'll write the characteristics of all these factors. The first factor, if you look at this, it's a straight line with a slope of minus 20 dB per decade, but it is passing through some 20 log k. So what's the k value here? 6. Okay. At omega equal to 1. So this is the characteristic of our first basic factor. What is that? So I'll write it here. So basically 1 by j omega is k by j omega whole to the power of r. You recall that basic factor. I'll write here. It's a straight line with a slope of minus 20 dB per decade. So what's the meaning? So for every multiplication of the 10, we have decrease in the magnitude by 20. So decade. So what is the value at omega passing through the value 20 log 6. So value 15.56 dB. At what's the point here? At omega equal to 1. Right? So if you have any questions at this point, you can ask. I wrote one statement. It's a straight line with a slope of minus 20 dB per decade, passing through 20 log k, where k equal to 6 here. So if you find the value 20 log 6, it is 15.56 dB at omega equal to 1. Right. So let us continue this. So what's the phase angle? It's a constant at minus 90 degrees. This is about first basic factor. So next basic factor, it is of the type 1 by 1 plus j omega t. So when omega 1 equal to 1, it has some corner frequency. That is before omega 1 equal to 1, you have one line with 0 dB per decade. And after 1, you have one more line with slope of minus 20 dB per decade. Isn't it? You recall that? So I'll write it here for omega less than omega 1. is equal to 1 here. It is a straight line of 0 dB. Then for omega greater than omega 1, which is 1 here, it is a straight line with a slope of minus 20 dB per decade. Okay. Now what's the phase angle? Phase angle varies from 0 to minus 90 degrees, right? And yet omega equal to omega 1, that is 1 here, your pi value is minus 45 degrees. We found this one. So this is about 1 by 1 plus j omega, that is pole value. Next value is 0. So here again, it's a 0 single pole. We have 2 straight lines before 4, after 4. So before 4, again it's a straight line with 0 dB. After 4, it's a straight line with slope plus 20 dB per decade. Since it's a 0, we'll get a plus value. So I write it here, same for omega less than omega 2, which is equal to 4. It is a straight line, I write it here, straight line of 0 dB. Right. For omega greater than omega 2, that is after 4, again it is a straight line of plus 20 dB per decade. Okay. So what's the phase angle here? Phase angle varies from 0 to plus 90 degrees. So at omega equal to omega 2, that is at 4, your pi value is 45 degrees. So this is about third basic factor. Fourth one, again it has 2 straight lines before corner frequency, after corner frequency. So let me write here, for omega less than omega 3, which is equal to 6. Again, it is a straight line of 0 dB. You remember, these are all approximated straight lines. For omega greater than omega 3, which is equal to 6. So what's the value? It is a straight line of minus 40 dB per decade. Right. What's the phase angle? If we find the phase angle for this, phase angle varies from 0 to minus 180 degrees, and at omega equal to omega 3, that is 6, your pi value will be minus 90 degrees. So this is how we can plot the table for the given basic factors. So this is about magnitude plot. Now we are ready to plot the magnitude plot on the graph sheet. So, but we don't have a graph sheet. Let us take the whiteboard only. So if possible, I'll try to get it a semi-large paper online. We completed the magnitude plot writing. Then let us look at the phase angle values. Okay. So let us look at the phase angle values now, our phase plot. We summarize all these things. Phase plot. So phase plot is I is equal to angle of 6 by j omega into 1 plus j omega by 4 by 1 plus j omega into 1 plus j into 0.3 by omega 6 minus omega 6 whole square. Now what is the phase angle for this transfer function? The phase angle would be first one, it is minus 90 degrees. It's a constant. So minus tan inverse omega, again minus tan inverse 0.3 into omega by 6 by 1 minus omega by 6 whole square plus tan inverse omega by 4. So this is about the phase angle of the given transfer function. So as the first term belongs to our first basic factor, second basic factor, and of course third basic factor we wrote it at the end, and fourth one is minus tan inverse. So I think you know this imaginary term by real. So let us find the values. When omega equal to 1, the phase angle is minus 123.91 degrees. When omega equal to 4, your phase angle would be minus 40.8 degrees. When omega equal to 5, your phase angle is minus 157 degrees. At omega equal to 5.5, your phase angle would be minus 176 degrees. And when omega equal to 6. Your phase angle would be minus 204.2 degrees and omega equal to 8. Your phase angle is minus. Should calculate all these values degrees, right? So this is about phase angle plot. So let us define few terms used in our Bode plot. That is gain crossover frequency, phase crossover frequency, gain margin, and phase margin. So generally they last for these four terms. One is gain crossover frequency, second one is phase crossover frequency, third one is gain margin, fourth one is phase margin. Right? So after defining all these terms, we draw the Bode plot for the given example number 1. So let us define first one. Which is gain crossover frequency. Second one, phase crossover frequency. So it is denoted as omega g, and this is omega p. Phase and gain. Third one, gain margin, is denoted as gm. Fourth one, phase margin, is denoted by pm. Okay. So let us define one by one. The first one, the gain crossover frequency is defined as the frequency at which the resultant magnitude is 0 dB. That is, the gain crossover frequency is defined as the frequency at which the magnitude of g of j omega and h of j omega is equal to 1. So let me write it here. It is defined as the frequency at which the resultant magnitude is 0 dB. So this is the key point. The frequency at which the magnitude is 0 dB. So that is, what is that? What does it mean? That is, the gain crossover frequency is defined as the frequency at which the magnitude of g of j omega into h of j omega is equal to 1. So this is the definition for gain crossover frequency. So second one, very important here, magnitude. So it is defined as the frequency. Remember, it's all frequencies: gain crossover frequency, phase crossover frequency. Right? Margin is different. The phase crossover frequency omega p is defined as the frequency at which the resultant phase angle is minus 180 degrees. So that is the phase crossover frequency is defined as the frequency at which the phase angle of g of j omega into h of j omega must be equal to minus 180 degrees. Let me write here, which is at magnitude. I'll write it here. It is omega. It is defined as the frequency at which the resultant phase is minus 180 degrees. That is the phase angle of j of j omega into h of j omega must be equal to minus 180 degrees. Okay. You must remember these 2 points. Third one, gain margin. I'll simply write it here to understand this. Gain margin is always 0 minus resultant magnitude in dB at omega p. I'll write it here. Here we define omega g, and this is omega p, and this is your gain margin. So this is very good. Here to omega p. Simply, you take the difference between 0 dB line and you draw a line from phase crossover frequency to your magnitude. You take the difference, you'll get the gain margin. And also remember, for stable system, your gain margin is always a positive value. If it is negative, it is unstable system, and it is equal to your frequency. That is at gain crossover frequency. It would be omega g equal to omega c. It is marginally stable system. Right. Fourth one, phase margin. Also, I don't write any complicated words. I simply write it as phase margin is equal to resultant phase in degrees at, I'll write it here, gain crossover frequency minus of minus 180 degrees. It's the difference. Or I can write it as this would be. So what is the resultant phase angle at gain crossover frequency? It is called phase crossover frequency. I can say it would be let us say it is pi plus 180 degrees. Okay. So what is this pi? I'll write it here. What is pi here? Pi is equal to phase angle of g of j omega into h of j omega at omega g. Okay. So these are the basic definitions used in the Bode plot. So generally, you might be asked with these questions. So it's the gain crossover frequency, phase crossover frequency, gain margin, phase margin, right? Sometimes they don't give k value. They just give k multiplied by some transfer function. In that case, first take the k is equal to 1 and then proceed for drawing the Bode plot. After that, you find out the gain crossover frequency or gain margin and all other parameters. Again, substitute those values for getting the k value. That is, you'll get the gain crossover frequency at k equal to 1. So then you substitute that value for getting k value. So we'll see with an example later. Let us look at our example number 1. Now, what is the example number 1? We completed the theory part of the Bode plot till this point. We defined, we got few more definitions here. We have phase angles here, and then statements of the magnitude plot. So based on all these points, let us quickly draw the Bode plot. So as I mentioned earlier, your plot should be drawn on the same graph, both phase plot and magnitude plot. So that's why we'll get the gain margin, phase margin, right? Gain crossover frequency, phase crossover frequency. Okay, so let us draw the graph. This is magnitude in dB. This phase angle by degrees. So let us put it here. Plus 20, plus 40, 0 dB line, minus 20, minus 40, minus 60 degrees. And then start this here, 0 degrees. Oh, let us move it to upward. I want to make it as a straight line so that I can right. This is 0 degrees. Maybe I can take it as 90 degrees minus 180 degrees. Minus 270 degrees, right? Now, let us put the first point. So the first point in our graph, the first point is magnitude plot. So I hope I let it here. So it's log omega. The first point is, it is 0.1. I can otherwise I can put it as 1 or some value. So let me take 0.1 here, 1 here, 10, maybe 100, and so on, 1000. Right? What's the first basic factor? First basic factor is wait, it is taking some time. Yeah. Just look at your table. So burst phase factor is, it's a minus 20 dB per decade line through, sorry, it is 20 log K, 20 log 6 is equal to 15.56 at omega equal to 1. So what's the point? At omega equal to 1, it is 15.56 dB, right? So at omega equal to 1, it is 15.56 dB, and also it is a minus 20 dB per decade line. Remember these 2 points. So let us put the points here. So at omega equal to 1, use another color, it is 15.56. So from here, I can divide it 1, 2, 3, 4, and 5, right? So 15.56 dB means it is somewhere here, right? If you calculate each point as 5 dB, 5, 10, sorry, this could be the, so I'll write it here, 5, 10, make it clear, should be 5, 10, 15, plus 20, 25, 30, 35, 40. Okay. So 5, 10, 15, it's almost here, right? So we'll have a point here. It's a point value. It is minus 15.56 dB at omega equal to 1. Okay. Now I should draw a 20 dB per minus 20 dB per decade line. How do you draw? Is the key point here. My God, I'm writing mistakes today. Right. So let me take one example here itself. 0, 20 dB, 1 here, 10 here. So when omega equal to 1, it is say 0 dB. And when it is some value, that is a 0.1, it is 20 dB, right? So it is going like this. So this is minus 20 dB per decade, right? Okay. So this is at 0 dB, magnitude is 0 dB, omega equal to 1. At 0.1, it is 20. So maybe you may have minus 20 dB here, right? Minus 20. Now look at the difference. You have minus 20 dB decay, 20 dB magnitude difference. So here the first point at omega equal to 1, it is 15.56. At omega equal to 1, it is 15.56 dB. Now what would be the value before omega equal to 1 and after omega equal to 1 when it is 20 dB scale? Right. So just add 20 dB for this, it would be 35.56 dB. That is at 0.1. At omega equal to 0.1, this would be definitely 35.56 dB. So that is almost here. Okay. Now before that, at some point not 1, so I can say it is 0.1 not one. It should be something like again at 20 dB, I'll get 55.56 dB, right? So it's a 0 dB line. So it's not omega equal 0. It's a 0 dB line. Remember, this is 0 dB. It's not omega equal 0. This is 0 dB value. I'm mentioning it as 0 dB. So here, let us take this value as something like 0.001. So this would be just extend this, and let us say it is plus 60. So this would be something like 55.56. Right? So this is how you should draw the minus 20 dB per decade line. So we need not go further, just draw a minus 20 dB per decade line, which is passing through this point. So this is your first asymptote, 20 dB per decade when omega equal to 1. Right. So what is happening? Why we stop at this point when omega equal to 1? It's a corner frequency, isn't it? Look at this. At each corner frequency, we should calculate the slope of the asymptote. So look at this. We have corner frequency 1, 4, and 6. So before 1, it is a 0 dB line, right? Before 1, it's a 0 dB line, right? It's a straight line, 0 dB line. So if you add this 0 dB plus previous one, you will get the current one. So 0 dB, it is minus 22. So you will get the same value for asymptote line till omega 1 equal to 1. So after that, what is happening? You are getting one more slope, which is a straight line with slope of minus 20 dB per second. So after 1 and to the next corner frequency, till the next corner frequency. What's that? Next corner frequency is 4 here. So till that point, the slope would be minus 20 dB, and the previous one it is minus 20 dB, right? So it would be minus 40 dB per decade between the corner frequencies 1 and 4, right? So here it is minus 20 dB per decade, a straight line, and between 1 and 4 it is minus 40 dB per decade. And after that, you look at this third one, less than 6, it is again a 0 dB line. So you'll get the same value here, previous one. So the next value would be minus 40 dB, right? So if you look at it, is plus 20 dB. So plus 20 dB minus 40 dB. So at this point, it is changing. It is minus 20 dB per decade at this point. That is from 4 to 6, it is minus 20 dB per decade. So after 6, minus 20 minus 40. So it would be minus 60 dB per decade. So this is how you have to calculate the slopes of your asymptote lines. I'm just summarizing all these points. First, you need to find out the slope of your magnitude line or asymptote line. So for the first case, it is minus 20 dB per decade. Then next, it is valid till the next corner frequency. The next corner frequency here, it is omega equal to 1. So till that point, it is minus 20 dB per decade. But what is happening here? We added minus 20 dB per decade after omega 1 till the next corner frequency, that is 4. So it would be minus 40 dB per decade. Again, at the 0 value, we are adding plus 20 dB per decade. So it would be, so if we add here it will be minus 40 plus 20. So this is minus 20 dB per decade. So now minus 20 dB and minus 40. Minus 40. Down here I'm getting some errors today. Minus 20 dB. Okay. Anyway, you remember 20 plus 40. It is simply I'm writing 60 minus 60 minus 20. Okay. We'll stop here. Minus 60 dB per decade. Okay. So if you have any questions, you can ask. We'll continue this. So we'll find the phase margin gain, crossover frequency, phase crossover frequency of this value. Okay. So, yeah. So till this point, I'll stop here. If you have any questions.